molecule, and then times exponential of gamma times little r over rho. So this factor here basically gives how the potential depends on the bond length of the BC molecule, right? Displacement of the BC bond length from its equilibrium. Okay, and so this big R, this can take on small values or large values, right? Because the A molecule starts out far away and then it comes in and it scatters at a very short distance. But in general, we're going to consider, we're not going to consider any bond breaking of the BC molecule. We're only considering vibrational excitation. So this little r, this is going to be a small number. And so therefore, we can replace this this third exponential with just the first few terms in the Taylor series expansion, because the argument is going to be small. And so therefore we can say this potential here, it's approximately equal to A times exponential of gamma R equilibrium over rho times exponential minus R over rho times the Taylor series. And Taylor series of exponential of x, if x is small, it's 1 plus x squared plus dot dot dot. So assuming r is very small, we'll just use only the first and second term of the Taylor series. So okay. Okay, so our next task then, if we're going to apply semi-classical mechanics, we want to know what is this matrix element, right, for the time-dependent perturbation connecting the initial and final state. So the perturbation matrix element V final initial, by definition, that's just the integral of the final state wave function complex conjugate times the interaction, V of t, right? And V of t is this expression here. Right, so it's okay, sorry, I've made a mistake in my notes. So it's and then we take the the initial wave function, and we integrate dr. Okay, and so this is going to be equal to, so the integral is only over the little r, and so basically we're going to get A times exponential gamma R equilibrium over rho times exponential minus R over rho, right? This stuff can all come out of the integral. And then we're going to get an integral so there's two terms remaining here. So we're going to get psi final star times psi initial dr, and then we're going to also have a term that goes as psi final star, let me write it like this. Gamma over rho, psi final star, r, psi initial, dr.
In the second term, this equation, minus r by,
Where?
give us minus r.
This one?
No, no,
After
minus r in the denominator.
Big R or little r?
Capital R.
minus r by rho.
Capital R.
What about it?
Is it wrong?
That comes from here. What's the question?
Oh, I was like looking, it's different term than rho.
It's rho.
Oh, yeah, sorry, this is a row. Maybe I didn't write it clearly. Does that answer your question? Okay. Okay, so this integral is easy, right? This one is equal to 0 because we're assuming that the basis states are orthonormalized, and so the overlap integral between the initial and final state is 0 if they're different states. But this one, this is going to be non-zero, and you know, we can give it a name. Maybe you can call this integral here rho final initial, because it's going to have units of distance. And if you've taken a course on vibrational spectroscopy, this integral actually looks familiar because basically if you have a dipole transition between one vibrational state and another, like you would encounter in IR spectroscopy, usually the transition moment is proportional to the matrix element of the distance operator, which is what this is. And so if you have a harmonic oscillator, this integral is actually has a selection rule of delta V equals plus or minus 1. So it can change the vibrational quantum by plus or minus 1. In general, you can also have non-zero transitions between states that don't have delta V plus or minus 1, because you could have anharmonicity of the oscillator, or you can have, you know, if you include higher order terms that we're neglecting here in this expansion, that'll also give you higher, you know, delta V plus or minus 2, plus or minus 3. But in general, this is going to be large for delta V plus or minus 1, and much smaller for higher delta V transitions. So the most likely outcome of a collision is going to be that you change the vibrational quantum number by plus or minus 1. Okay? And so then, let's see, we can write our V Fi, right? This is going to be a function of t, and it's going to equal a times this rho Fi integral, right? This integral here times gamma over rho times exponential of gamma r equilibrium over rho, right? So this is all just a constant. And then we have exponential of minus r of t over rho. Okay? And so all these constants, I'll just group them together and call that C. Okay? Maybe if I switch markers, it'll be easier to read. Maybe this marker is a little better. Okay? So basically our approach when we apply semi-classical mechanics is the R of t right, we're gonna get that using classical mechanics, and then we're using quantum mechanics to figure out the change in quantum state. So if you assume a simple trajectory where r of t equals the absolute value of velocity times time, then that would correspond to a situation where basically if you plot r versus t, then you have a collision partner, it's coming in, right? So r is decreasing linearly with time, and then at time 0 there's a collision, and then at time greater than 0 the collision partner is going away with the same speed. Okay, so this would be a very simplistic r of t, but for our purposes it's good enough. So then, if we make this assumption, then so our next goal is to calculate the probability of a transition from state I to state F. And using semi-classical mechanics, we're going to do that using this equation. So we take this perturbation matrix element that we just derived, and we have to integrate it multiplied by e to the minus I times omega t, where omega is the difference in the initial and final energies divided by h bar. Okay, so this is going to equal the square of the final coefficient at time infinity, which is given by the integral, or it's proportional to the integral. So we're going to have c over I h bar times integral minus infinity to infinity e to the minus velocity times absolute value of time, assuming velocity is a positive number, over rho times e to the minus I, or I'll call this plus, e to the I omega t dt, and then we have to square it. Okay? And so we have basically an integral between two factors. So what do these two factors look like? Well, if you plot this one, right, this factor here, right, e to the minus v t over rho versus time. Basically, this is an exponential decay, a two-sided exponential decay function, right? So it looks kind of like this, right? As t increases, this decays, regardless of whether t is positive or negative. Okay? And so the characteristic distance of the decay is going to be rho over v. Right? So the distance parameter for the interaction divided by the velocity. So this is like the interaction time. This is the amount of time that the collision is going to take. And this other factor here,
Professor,
yeah,
t is the time.
that's correct.
But why we have a negative time? What does it mean?
Oh, well, the collision happens at t equals 0. So the time before the collision is negative,
Oh, okay.
and then the collision happens, and then it's positive time. So this integral here is from negative infinity to infinity, and the collision's in the middle at t equals 0.
Okay, so basically 0 collision time.
Yeah. So the second thing here, right? This is just an oscillating function. So if you plot its absolute value, it looks like a sine wave. And so basically, let me just rate the key conclusion, and then we're out of time. And then next time I'll finish up with this example. So the key conclusion is if v over rho is much, much less than omega, then the probability of the transition will be 0, because basically, so if v over rho is small, that means the collision time is long, and that means that this function is basically very flat. And so if you take a flat function and multiply it by an oscillating function, you get oscillating amplitudes, positive, negative, and they all cancel each other. Okay? But if v over rho is greater than or equal to omega, then you end up with a significant probability, significant, sorry, bad handwriting. Because basically if rho over v is very narrow and it's equal to 1 oscillation period or less, then you're just going to basically multiply everything by 0 except for 1 period of oscillation, and then you're going to get some non-zero quantity. Okay? So we're out of time, but any questions?